Hello everyone. Welcome to the ROSE project of Rayat Shikshan Samstha Satara. Uh, in mathematics, my topic of representation is definite integration. Myself, V. Rene, I am from SGM College Karad, and this is my lecture number 3. And my topic of representation is definite integration. So, in this lecture, we are going to see some typical results and problems based on that results. Result first is integral a to b f of x divided by f of x plus f of a plus b minus x dx is equal to 1 upon 2 b minus a, and we are going to see second result, that is this result is known as reduction formulae. To evaluate the integrals of the types integral 0 to pi by 2 sine raised to n x dx and integral 0 to pi by 2 cos raised to n x dx, such results are used and these results are known as reduction formulae. So, what are these results? So, let us see. Integral 0 to pi by 2 sine raised to n x dx. It will be reduce this n. If n is odd, then reduce n like this: n minus 1, n minus 3, n minus 5 up to 4 to dash dash dash. Last term will be 2 by 3. And if your n is even, then reduce this n like this expansion. So term will be n minus 1, n minus 3, n minus 5, dash 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 up to pi by 2. This will be your last term. And if your term is integral 0 to pi by 2 cos raised to n x dx, then we everyone knows that what is the relation between sine and cos. So cos pi by 2 minus x, it will be sine x. So whenever you have to find the integral 0 to pi by 2 cos raised to nx dx, this term will be taken as integral 0 to pi by 2 cos pi by 2 minus x bracket raised to nx dx. So cos pi by 2 minus x, it will be sin x. So you have to take sin x raised to n into dx. So this term will be sin raised to nx dx, and we already have seen the formula for integral 0 to pi by 2 sin raised to nx dx into these two steps as this: if n is odd and when n is even. So you can apply this reduction formula to sin raised to nx dx also, and for integral 0 to pi by 2 cos raised to nx dx also. Then next we are going to see examples. Example first is evaluate the integral 0 to pi by 2 root cos x divided by root sin x plus root cos x dx. So let us consider this integral as I. So let I is equal to this given integral, and we call this as equation number 1. So we are going to use the property f of x dx is same as f of a minus x dx, and integral is from 0 to a. So by that property that we have already seen in previous lecture, we are going to replace this x with the value pi by 2 minus x. So in these three terms, we have to replace this x with the term pi by 2 minus x. So this step will appear. Then after calculating these terms, we get cos pi by 2 minus x is sin x. Similarly, sin pi by 2 minus x will be cos x, and cos pi by 2 minus x will be sin x. And we call this as equation number 2. So after adding these two equations, that is equation 1 and 2, in LHS we get I plus I, that is 2I, and in RHS we have integral 0 to pi by 2 Observe these two equations. In these two equations, numerator and denominator are same. So only one term remains here, that is integral of dx. So integral of dx will be x, and by applying the limits 0 to pi by 2, we get the term pi by 2, and we want the answer of I. So transfer these two in RHS, we get I is equal to pi by 4 as final answer of this integral. Then we are going to see our example 2. What is example 2? In example 2, we have given that integral 2 to 3 root x divided by root 5 minus x plus root x dx. So as usual, let I is equal to this term and we call this as equation number 1. So I is equal to integral 2 to 3 5 minus x divided by root x plus root 5 minus x dx, and we call this as equation 2. How this step will occur? In this step, we have replaced this x with the value 2 plus 3 minus x, that is 5 minus x. So replacing this x, all three terms of x with the value 2 plus 3 minus x, we get these steps and we call this as equation number 2. So by using this property, we have replaced this x with the value 2 plus 3 minus 6. So after adding these two terms, that is adding 1 and 2, we get in LHS I plus I, that is 2i, and in RHS integral 2 to 3 root x plus root 5 minus x upon root 5 minus x plus root x dx. So this numerator and denominator term is same. So only one term remains here, that is 1. So we have to find integral 2 to 3 integral 1 dx. So our final answer will be 1 by 2. Then we will go to our next example, that is example 3. Third example is pi integral pi by 6 to pi by 3 dx upon root of 1 plus dx upon 1 plus root of cot x. So let I is equal to this given integral. Then in next step, we are going to convert this cot x into cot x is cos x by sin x. So after simplification, we get this step and we call this as equation number 1. So how this equation number 2 appears? So for this equation number 2, we have to replace this x with the value pi by 3 plus pi by 6 minus x, that is pi by 2 minus x. So when you replace this x with pi by 2 minus x, similarly here also and here also, then we get instead of sin x, we get cos x. Instead of sin x, we get cos x, and instead of cos x, we get sin x. So in next step, as usual in previous example, we have added equation 1 and 2, and after adding 1 and 2, in LHS we get 2i. 2i is equal to, in here it remains integral pi by 6 to pi by 3 and integral of dx. So after finding integral of dx, that is x, and applying the limits pi by 3 and pi by 6, we get this term as answer, and the final answer will be I is equal to pi by 12. Then we move to our next example, that is example 4. Example 4 is we have to evaluate this integral. This integral is from pi by 5 to 3 pi by 10 sin x upon sin x plus cos x dx. So let us solve this problem. Let I is equal to given integral and we call this as equation number 1. And for this example, we are going to use the property integral a to b f of x dx is equal to integral a to b f of a plus b minus x dx. So you have to replace this x with the value a plus b minus x dx. So in this example, you can observe that here a is equal to pi by 5 and b is equal to 3 pi by 10. So you have to replace the x, the variable x with the value pi by 5 plus 3 pi by 10 minus 6. So we get the step as I is equal to integral pi from pi by 5 to 3 pi by 10, and the values of x will be replaced by this value. So this step appears. Then after calculating or after simplification, we get the I is equal to integral with that limits, and after calculating we observe that this term will be pi by 2. So here it is pi by 2, same here also, and same will be here also. So after applying the formula sin pi by 2 minus theta and cos pi by 2 minus theta, this term of sin changes in cos, and this term of cos will be changed in sin x. So we call this as equation number 2, and as usual, as in previous example, we are getting to add equation 1 and 2. After getting added equation 1 and 2 in LHS, we get I plus I, that is 2I, is equal to, this is our first integral plus this is our second integral. So in both the integrals, their limits or their integrals are same, and also their numerator and denominator is same. So this value gets appear, and you will find the value is remains is only integral 1 dx. So integration of 1 dx is x, and you have to apply the limits here. Then after applying upper limit value minus lower limit value, this step will appear, and in after doing calculation on these two terms, the term appears is pi by 10. So transfer these two in RHS, we get I is equal to pi by 20. So now we will move to our next example, example 5. What is this example? This example is evaluate the integral 0 to a 1 upon x plus root of a square minus x square into dx. So let I is equal to this term, that is given integral. Then to solve this integral, we are going to apply the method, substitution method. So we are using the substitution for x, that is we are going to put x is equal to a sin theta. Then after derivating this term, we get dx is equal to a into cos theta d theta, and for this term in square root of a square minus x square, this term will be changed as like this, a square as it is, and instead of x you get the term a square sine square theta. So after taking a square common in both the term, we get square root of a square into bracket 1 minus sine square theta. So in next step, 1 minus sine square theta gets replaced by cos square theta, and after taking the square root of this term, we get a cos theta instead of square root of a square minus x square. Now we will see what about its limit. Its limits are also gets changed by substitution. So when x is equal to 0, we get theta is equal to 0, and when x is equal to a, we get theta is equal to pi by 2. So our integral becomes I is equal to integral 0 to pi by 2 a cos theta d theta upon a sin theta plus a cos theta. So the value of a in numerator and denominator gets cancelled here, and the term remains only is cos theta upon sin theta plus cos theta into d theta. So we call this as equation number 1, and for this we are going to use the property integral 0 to a f of a minus x dx. So we are going to replace this theta with the value pi by 2 minus theta. So after replacing the value theta with the value pi by 2 minus theta, we get I is equal to integral 0 to pi by 2 cos. Instead of theta, we have written pi by 2 minus theta in three values, here also, and here also. So after taking the values of cos pi by 2 minus theta as sin theta, similarly here also sin theta, and for sin pi by 2 minus theta, the value will appear as cos theta, and we call this as equation 1. Then in next step, we are going to add equation number 1 and 2. So in LHS, I plus I, that is 2I, and in RHS, these are two terms that we are going to add. So here the integral limits are same. So we have taken the integral and we observe that numerator and denominator is same. So the value remains is only integral 0 to pi by 2 1 d theta. So its answer is theta, and now we are going to apply these two limits. So by taking its limits, we get pi by 2 minus 0. So our answer will be pi by 2. So the final answer is I is equal to pi by 4. Now we will move to our next example, example 6. In example 6, we are going to evaluate the integral 0 to pi x upon 1 plus sine square x dx. So we call this as I, and we call this as equation number 1. In this example, we are going to use this property. So we are replacing this x with the value a minus x. Here the a will be pi. So we are going to replace this x with the value pi minus x. So our step will occur like this. Instead of x, you are using pi minus x. Here also, instead of x, you are using pi minus x. So your integration becomes like this. Instead of sin pi minus x, you have sin x. So this step appears. So I will be integral 0 to pi divided by 1 plus sine square x dx. You can write these integrals as like this with the previous properties. When you changes its limit, the value gets minus sign. So this step appears. So you have this value is the value of I. So instead of this, you have written I, and from equation 1, you get this step as I is equal to integral 0 to pi upon 1 plus sine square x dx minus this will be the value of I. So by transferring this I in LHS, you have 2I is equal to, and from this first value, you have taken pi constant outside of integration and remaining value as it is. So to solve this integral, we are now going to divide the numerator and denominator by cos square x dx. So after dividing by cos square x, we have 1 upon cos square, that is sec square. Similarly here 1 upon cos square is sec square, and sin square upon cos square, that is tan square. So pi as it is, and instead of sec square x plus tan square x, you have written or you are using the identity, one of the identity. Then by using that identity, you get this term in the denominator. So you have this value remains. So to solve this integration, again we are going to use the substitution method. So we are going to put t instead of tan x. So after deriving this term, we get sec square x dx as dt, and your limits of integration will also get changed. When x is equal to pi, we get t is equal to 0, and when x is equal to 0, we get t is equal to 0. So your this integral value becomes 2I is equal to pi as it is, and these two limits are 0 to 0. So here 0 to 0 integral dt upon 1 plus 2 dt square. So we will see that here upper limit and lower limit both are 0. So answer of this term will be 0. So final answer I is also equal to 0. So that's all about today's lecture. Thank you.